Hello, my name is Ahmed Jamshidfar. Today I'm going to show you how to solve static equilibrium problems. Uh, we start with the static problems in 2D when we are facing with x, y dimensions, and we have everything in planar configuration, like the problem that we have here. We have a distribution of load, two cables connected to a beam, and a joint at the point C. Generally, when we are dealing with static problems in 2D, we have three main equations, and as you can see, we have sigma of x, sigma of y, and sigma m equal to 0. As you can see here, we have three equations, and you should know that at most we can have three unknowns. And for finding our unknowns, we need to find the free body diagrams of static parts. Here I have an example, and I want to show you how to find the free body diagram of this beam here, and try to find the number of unknowns. Okay, let's go ahead and try to do it together. For developing the free body diagrams, my approach is like this. I take a scissor and try to cut whatever is connected to the beam. I mean, cut this cable, and get rid of this joint, and put the role of these things, or the reaction, or the forces that they can apply on the beam. Okay, I start with the cable. As you may know, the cable is applying only tension. Then when you're removing this cable at this part, you need to put the role of that cable, which is a tension in direction of that cable. This is the first thing that we get rid of that. The second thing is this cable. This is connected also to the beam. I get rid of that and put the role of that, which is another tension, and then go to the third thing, which is a joint. We name it hinge, and we put the reactions over there. Name one of them CX, the other one CY. Okay, here let's name one of these tension T1, the other one T2. As you can see, if I consider this as the free body diagram of the system, I have four unknowns, but here actually here I have a pulley that can help me to reduce the number of unknowns. If we consider pulley and consider the cables, we would have T1 and T2 here. The point is that if these two values are different, the pulley start to rotate, and that's not static anymore. That means it's dynamic. When we are solving a problem in static equilibrium conditions, everything is actually nothing is moving, and that means this disk would be in static equilibrium conditions as well, meaning that T1 needs to be equal to T2. This equation is helping me to reduce the number of unknowns. Actually, I put these two values equal to t, and here I would have only one unknown, name it t. Okay, I erase some part of this page to provide enough space for myself, and continue to show you what would be the approach here. Okay, right now I know I have three unknowns and three equations. Then I would be able to solve this problem. Okay, the question here is that how I realized that put only Cx and Cy here, or a tension for the cables, only one single tension over there. These are the reaction forces, and there are some tables in the textbooks which are written for the statics or mechanics of materials or similar courses. Based on that, we can realize what to put instead of any object. To give you an idea about that, my approach is like this. I try to consider, for example, a single joint and see what motion is possible for the connected rod to that. For example, here, if you start to and want to move this connected rod to this joint and push it upward, it is impossible for this guy to move. And if you start to move it to the right, it is impossible as well. These are the reaction forces, and we don't know the value of them, but we know they exist. But if you start to rotate this guy, it is possible to rotate this guy, and that's why I don't have any moment here. Okay, the same story for the cables. The cable can apply only tension. If it goes under compression, it's not static anymore. It starts to get a slack and it moves actually, and that's why we put only a tension here. The same story here, and that's why we put only a single tension in direction of the cable and exactly in direction of that cable. That's how I realized to put these guys there and no other unknowns here like M. Okay, here I have all the possible joints in 2D, which can be in different problems or questions and you may face with. I start with the first one, which is a roller, and in the roller case, if you start to move this guy in the move it to the right or left, you are able to do this because there are some wheels over there and it is possible to move this guy. Also, if you have a frictionless surface, you can do it easily, and there is no force here to prevent you from doing that. But if you start to move this guy upward or downward, it is impossible. Also, we consider the same story here, and there is a force over there which is preventing you pushing this guy down, and there is a ground thing over there which is preventing you from doing that. The same story for these guys, and that's why we have only a single force over here, and that force would be the reaction. That means in the cases that you have a roller, you put only one unknown over there. In the case of having a short cable or short massless link, you put only a force over there. In many cases, you can read that the mass of this part is negligible in many questions, and that means the same as cable. And in these questions, you put only a single cable, a single force in direction of the connection point of these. Actually, a line which is connecting these 2 points together. For the cases that you have a friction pin in a slot or a collar on frictionless rod, you would have the same story. You would have a force which is perpendicular to the line of slide and slot actually. For the cases that you have a hinge, you would have two unknowns. That means if you start to move this guy to the left or right or up or downward, it is impossible to move this, but it is possible to do the rotation. That's why we don't have any moment over here. These two unknowns can be, for example, Rx and Ry here, or the magnitude of the force and the angle. The magnitude of the force and the angle of that are two unknowns here. The same number of unknowns here. It depends how you write down the equations, but the number is the same. And also, if you have a rough surface, means you have friction, which is preventing you from moving to the left and right. You have two unknowns. One which is preventing you from penetrating to the ground or surface, and the other one is caused by the friction over here. In the case of fixed support or welded one, you would have two unknowns. That could be Rx or Y and M, which is preventing you from doing rotation here, and that could be the magnitude of the force, the angle of that, and a moment which is applied on this guy. And in these cases, we have three unknowns in our equations. And depending on the problems, you can use this table to see which one is which and how many unknowns you need to put there. Okay, so in case of 3D statics, meaning when we have a problem in 3D and not only x and y plane, we are dealing with 6 equations, 3 of them for the force and 3 of the other 3 for the moment. And in these cases, the thing is that when we start to draw the free body diagram for different parts, we need to know the reactions for different joints. Here I have an example which is connected to the wall using 3 cables, and there is a load in the middle of this part which is trying to pull down this joint, which is hinged at point O. Actually, we have a ball and socket at this point, and some cables connected to different points of this rod. Here I'm trying to do my approach for free body diagram at the beginning. For doing that, actually I try to see which is connected to this guy and get rid of that at the beginning. For doing that, let's assume we have a scissor. I cut these 2 guys, which are 2 cables, and put their effects over there. One of them would be like this, for example, name it T of E. The other one would be T of D. Disconnect the other thing which is here. We all know that this guy has a weight which start bolts to pull down the rod. And if I get rid of that or cut it, I just put the effect of that, which would be 400 G as a weight over there. And in point A, I get rid of the cable, put the effect of that, name it T of C, and going to point O, we can read here that there is a ball and socket, joined at point O. Ball and socket is like a ball inside the socket, and as you can see, if you connect the rod to this ball, it is impossible to move this guy to the left, right, or up, down, or out of the plane, but it is possible to rotate this guy inside the socket in any direction. That means there are forces which prevent motion, translational motion, but there is no moment to prevent the rotational motion. And that's why we put only 3 reactions here, name it OY, OX, and OZ. Okay, this would be the free body diagram of this rod. Let's go ahead and review the number of unknowns. As you can see, we have 3 unknowns here, 3 forces and 3 tensions related to the cables. In total we have 6 unknowns here and 6 equations here, and that means that in general we can solve this problem using these equations. And but the question is that what about different joints? This is ball and socket. What about different rollers and different cables or slots? What we do there and how many unknowns we need to put there? To answer these questions, there are very good tables which can help you to find the reactions related to different joints. For example, here we have a frictionless contact surface. Frictionless means that this rod can slide in any direction, and there is nothing to prevent that, but it cannot penetrate to the surface. That's why we have F here, and you can rotate it in any direction. The only thing that you cannot do is penetrating to the surface, and that's why you have only one F over here. The same story if you have a roller, you have only one F over there. Ball and socket, as we discussed in the example, we have three forces which prevent translational motion, but you are able to do rotation whatever direction that you like. When we have truss bearings and a hinge with truss bearings, you need to know that they do not let you to do a sliding. That means if you have a shaft inside a truss bearing, you cannot do motion in this direction. That's why we have Fy over there. Also, it's fixed to the base or ground or whatever. It does not let you to do motion in this direction, which is Z direction, and also in X direction, and you cannot rotate this guy over around x and around z, but you can rotate it around itself, and that's why we don't have any my order. Actually, if you have some cases and some connections in your problems, what you need to know is that you have five unknowns over there, including 2 moments and 3 forces. In the case of frictionless hinge, you can figure out how does it let you move, and it's pretty similar to the previous case, and it does not let you do translational motion in any direction, and it just lets you do rotation around this axis. There's another similar thing to this. When you have a single hinge, you cannot move this upward, downward, left and right, and you cannot do any translational motion, and that's why you have 3 forces over there. The only thing that you can do is rotation around this axis. The other rotations are impossible. If you want to do that, you start to break down this guy, and that's why you have these reactions, and in total all of these guys have 5 unknowns. In the case of fixed support in 3D, what you would have is everything. That means you cannot do any motion for this guy. It's welded or fixed to the ground or wall, and that means you cannot do any translational motion and rotate it around any axis, and that's why we have 6 unknowns. Having the knowledge of these reaction forces, you can figure out how many unknowns and how many moments and reaction forces to put on the connection points, and start to match the number of equations and the number of the number of unknowns. And the key point in solving the static equilibrium problems in 2D and 3D is making sure that the number of the equations and the number of unknowns are the same, and if you can get them matched, you can easily find them, and you don't get lost, and you know, okay, it is possible to find these unknowns because I have enough number of equations, enough number of unknowns, and then start to write down and find for the unknowns. In the next videos, I try to show you how you can choose the best equations for solving, and how to start with which one of them, actually, meaning you have, in case of having for example 6 equations and 6 unknowns, which one is better to start with and make the solution easier for you, and you can save time by starting with that equation. That would be the topic of next video. Thank you so much.